Hi guys. Okay, so here's lesson 5. In lesson 5, we're going to learn about normal distribution and the empirical rule. Okay, so in this lesson, we're going to reminisce on when we learned about distributions. Remember, we learned normal distribution and then skewed left, skewed right, all that. Well, we're going to learn a lot about normal distribution in this lesson. Okay, so we're going to learn about the different properties of the normal curve. And we're going to remember or review a little bit of Chebyshev's rule or theorem. Sorry, remember that? Well, we're going to figure out what was actually good, what he did that was really helpful and what wasn't. And then we're going to look at the empirical rule and how we can use that with normal distributions, and then how to apply the empirical rule. Okay, so remember distributions. So we actually did use this data earlier, like at the beginning of the course. Okay, so we used this chart before when we were learning about class limits and frequency tables and all of that. Okay, so remember distributions and such, and using a frequency table. This can only be done with quantitative studies. Okay, so we can only use quantitative variables for this kind of thing. Remember what type of studies that is? Those are numerical. Okay, not categorical, numerical. Okay. Okay. And remember distributions. Okay, so of course using quantitative variables, we determine our classes. Remember? We do the math to figure that out. We figure out what our classes are. We make our frequency table. We make our frequency histogram, which is what we see on the right side here in this graph. And then we get to see what the distribution looks like. In this case, it is a skewed right distribution, right? This is not normal. Okay, so the empirical rule will not work on this because this is like a skewed right distribution. It's not a normal distribution. We can only use normal distributions for this, for what we're going to work on today. Okay, so remember normal distribution? We went over this like pretty much in the beginning of the course or of the semester. But so normal distribution, that's when it goes like this. That when your distribution kind of looks like that, where it's really tall in the middle and all that. Well, normal distribution is kind of how a lot of grades work, and so I figure we could just talk about, since grades are quite relatable as a student and a teacher, we all kind of deal with this. So typically, what usually happens, I mean, of course not in our class, because you guys are all really good and get good grades, but I mean, in a huge class, many times, especially if there's like a really difficult test or pretty darn difficult test, you might have normal distribution, okay, and that's quite common, okay, where your mean, your median, your mode, it's all pretty much up here somewhere, right? And most of it just sits right there, and then you have very few people who have good grades and decent grades, and just a few people who have terrible grades, and then it just kind of, you know, a lot of the people just sort of stick around this area. Okay, like the C is usually the most common grade in that situation. Okay, so let's look at some of the properties of normal curve. Okay, so we're using the exact same graph as the previous slide, and we're just going to look at some of the typical properties of a normal distribution curve. And none of these properties apply to any of the other types of distributions, so it does not apply to bimodal, skew left, skew right, anything like that. It only applies to normal distributions, okay? So first of all, the curve is always shaped like a bell, where the highest point is over the mean, okay? So the highest point is over the average. The average is somewhere around here, right? Somewhere within that frequency, okay, or that class. And the curve is symmetrical around a vertical line through the mean. Okay, so pretend So if this is the mean, we put a vertical line through the mean, and it's totally symmetrical. Well, not 100% of course, but I mean, for the most part, it gives you some sort of like a symmetrical, you know, thing. Like if we were to fold this in half, each side would be pretty much equal-ish. Also, the curve approaches the horizontal axis, which is the x-axis, this one right here, but it never actually touches or crosses it. So see how like it goes down on both sides, okay, and it starts to approach the x-axis, but it never quite touches it. Think of it like a romantic movie, or actually if you guys have ever seen a Bollywood movie, I mean, this is pretty much what they do. They get so close to each other, but they never do anything. Okay, so it gets really tense and passionate, but nothing ever happens. So then we have the inflection or transition points between the upward and downward, okay, and that occurs about sort of at the mean, but like plus or minus 1 standard deviation. So let me show you what I mean by that. You see how this is the peak and this is the mean, right? The part where it starts to droop down is what I'm talking about. So the next point where it's starting to go downward or upward if you're going this way, these areas, okay, this is occurs at about 1, like the mean plus 1 standard deviation. This occurs at the mean minus 1 standard deviation. Okay, so it's like that. Whatever you calculate your standard deviation to be, this should happen at whatever you calculate your mean to be plus a standard deviation, and this should be a minus a standard deviation. So I hope that kind of makes sense. And also finally, this curve, this entire curve, if we were to fill it in like I did here, the area of this entire curve should equal 1, okay? The entire thing should equal 1. So think about it at, like in a percentage, this should be 100%, this whole thing, okay? So if you could also say that like if we were to cut it in half, okay, if we were to kind of like what we did up there where we cut it through the mean, cut a vertical line through the mean, each side would be 50%, right? Each of these sides would be 50%. And, hold on. We could also cut a vertical line right here at 25%, and then this whole section would be what? 75%. Okay, so we can start thinking about this in terms, the curve in terms of like different percentages. Okay, like this over here would be 25%, you know, would be whatever falls in, whatever frequencies fall within that section. And then this could be 75%, and it's like whatever frequencies fall within that section. Of course, you can move this line on this side as well. There are a lot of things you can do with it, but just to kind of give you an idea, we can start thinking about this entire curve in terms of percents and portions, because, like I said, this entire thing equals 1 or 100%. Okay, remember Chubbs Theorem? Back then, when we first learned about it, we used this chart that showed us that we could use the standard deviation, and we can say, you know, if we choose to use 2 standard deviations, 3 standard deviations, 4 standard deviations, however many standard deviations we choose to use to figure out what our lower limits and what our upper limits were, it would correspond to a certain percentage of data that fall within the interval. Okay, I know that's kind of a lot, but we went over this a little bit before, so that's kind of like a refresher what Chubbs Theorem was. But if anything, please go back, and this is all in lesson 3.2. Okay, back when we learned about standard deviations. So if you need to refresh your memory, go ahead and refresh your memory. But Chubbs theorem had us using standard deviations, okay, and means. So what it would say was however many standard deviations you decided to use for your data, okay, that would tell us which percentage of the data falls within that specific interval. Okay, so, and this is basically how you would state certain things. So at least whatever percentage of the data fall within that interval. Okay, so if the lower limit is, oh, and remember mu? This is when we're using, this is going to equal the mean, but you use this when you're using like an actual population data. This is not what you use when we use samples. I know we're used to saying X bar, and that we use when we're doing samples. But in this situation, in the example that we're working on today, since we're working on a classroom of 100 people, we're not using a sample size, we're using the actual population, okay, the actual 100 students. So it's more appropriate to use mu and use this kind of OB6 as the symbol for standard deviation. Okay, so that's all this means. Just to let you guys know. Anyway, so how we use or find our upper and lower limits. Remember how we would do that. We would take our standard deviation, and we would, if we choose that we want to use 75% of data within the interval, we would have to use 2 standard deviations for this. And so that way you would find your upper and lower limits by taking your mean, which is your mu, okay, and then you're going to find your lower limit by adding 2 of your standard deviations, okay, and that's going to be your upper limit. And if you're going to find your lower limit, you're going to take your mu, which is your mean, and then subtract 2 standard deviations, okay, and that will give you your lower limit. Okay. So in this situation with our example with the 100 students, let's say your mean for the score on the test was 65.5 and your standard deviation was 14.5. Okay, in the situation where we maybe we want to use 2 standard deviations, okay, and we want, which is going to correspond to 75% of data within the interval. What that means is that how we're going to find our lower and upper limit is we're going to take our mean, our mu, which is our 65.5, then we're going to subtract it by 2 times our standard deviation, because we're using 2 standard deviations, okay? So, and then that will give us 36.5, so that's our lower limit. And then to find our upper limit, we're just going to take the mean again, and this time we're going to add, because when you find your upper limit, you want to add. When you're looking for your lower limit, you're going to subtract, okay? So now we're going to add 2 standard deviations, or 2 times standard deviation, okay? And then your upper limit for that is going to be 94.5. Okay, so what does this mean? This means if you have 100 data points, okay, or 100 students, at least 75 would fall between 36.5 and 94.5. So at least 75% or 75 student scores in this situation, because we only had 100 students. 75% of 100 is 75. Okay, so 75 students scores would fall between 36.5 and 94.5. Okay. So why are we even doing this? Chubbs Theorem, empirical rule, what the heck? See, the thing is that intervals, okay, you know, this whole, like these charts that we're studying, they have limits, okay? So they have limits, and we need to figure out where that is so that we can figure out exactly where our data lies, okay? It really helps us zoom in on the data and what's going on with the data, okay? And, okay, so we know that. Now, Chubbs Theorem, the thing about this one is it's almost like a generic theorem. It's a generic rule, I guess, that you can think of it as. Like, it applies to almost anything, to any distribution, okay? So it's way more generic. It's very less specific about the data, okay? So notice that when we work with Chubbs Theorem, we have to say at least this percentage of the data falls within these limits, okay? So already it's not very specific at all, and it's telling us a really large range. And I mean, you have to go down to 4 standard deviations to even get you know, 90-ish% of the data. Okay, so it's very generic. Okay, it's super broad. Figure out what your limits are. Okay, but I mean, it works. It's what we have. It's, you know, what we have to work with, since especially if you're not sure about the distribution, or if you're using maybe skewed left distribution, or if you have skewed right, bimodal, like any type of distribution, this will work for. Of course, like I said, your limits are going to be very broad. All right, now we're going to look at the empirical rule. Okay, so the empirical rule, this is only going to apply to normal distribution. So if you know you have normal distribution, great, wow. The empirical rule is going to be really, really useful for you, okay? Because watch, it gets very, very specific. So approximately is what, you know, is the term we want to use, because it's a bit more, you know, nothing is 100% sure usually. Or, well, I mean, anyway, approximately. Approximately is how we're going to approach this, but this gets way, way, way more specific than Chubbs Theorem. So it's way more useful, especially if you had normal distribution, like I said. So this is how it goes. Basically, this helps you out if you even have one standard deviation. Okay, if you have one standard deviation, you can find your upper and lower limits with the empirical rule, and it basically tells you that 68% of all your data is going to fall within that upper and lower limit. Just using one standard deviation, we didn't even have to go too far, so it's really narrowing down our data. Okay. Then, if we use two standard deviations, already we're way, way, way past Chubbs Theorem. After using two standard deviations, 95% of our data is going to fall within that interval, or, you know, within that upper and lower limits that we're going to calculate. Okay, so this is extremely useful if you have normal distribution. It can really narrow things down a lot for you. Now, if you have 3 standard deviations, if you use that, pretty much all of your data, it's going to tell you where all of your data, almost all of your data is going to fall. Okay, that's huge. All right, so that's 99.7%, which is really almost all of your data. So it gets very, very precise, or, you know, really narrows things down for you. Excuse me. Okay, so here is an empirical rule diagram, just to try to put a lot of this into perspective for you. Okay, so here's your mean at this point, right? Here's your mean. Okay, now if you've noticed, every single one of these sections has a symbol for standard deviation, right? What that means is that the width of this section, that is your standard deviation, okay? Or, you know, whatever symbol that you want to use. But that's what that means. That's standard deviation. So each one is the exact same width, okay? And that all equals a standard deviation. So if you look at the very bottom of the page, okay, of this chart, you'll see that each level, okay, we have our mean plus one standard deviation. Okay, now we have a mean, which is right here, our mean plus two standard deviations because you went forward two standard deviations. Over here we have our mean plus three standard deviations because we went forward 1, 2, 3 standard deviations. This one over here, I'm sure you can guess, would be one mean plus 4 standard deviations, right? And same thing going the other way. We have our mean here, okay, and then if we go over here, we have our mean minus 1 standard deviation because we're going backwards, so it's less than. So if you go this way, if you went you know, backwards 1 standard deviation, so it's our mean minus 1 standard deviation. Now this one is the mean minus 2 standard deviations because we moved over twice, moved over by 2 standard deviations. Now this one right here is going to be the mean minus 3 standard deviations because again we moved 3 standard deviations over, 1, 2, and then 3. See? And of course this one, I'm sure you can guess, would be the mean minus 4 standard deviations. Okay, so this is what all this means. Now, what do the percentages within this mean? That means that all of the points that fall in this section, that means that 34% of the data, okay, fall in this section. Okay, in this section, 13.5% fall within this section. This is using the empirical rule. Okay, and remember this only counts for normal distribution. And of course, here we have a normal distribution curve. That's why it's like this. But so each section, okay, so if we go over here, okay, at this point right here, from the mean, this covers 34% of your data at where you're, okay, at this point where your lower limit is the mean minus 1 standard deviation, okay, and at the point where you, so wherever your lower limit is the mean minus 1 standard deviation and your upper limit is the mean plus 1 standard deviation, that would be this entire section right here, right? If you look at it, that is 34% plus 34%, which equals 68%, right? Didn't we just see that at 1 standard deviation, that covers 68% of our data? Isn't that what we saw at the last slide? Yes, it is. That's what that means. So this whole section, 68% of our data. Just this section right here. Of course, that means where your lower limit right here. Yeah, this is your lower limit. This is your upper limit, and that would mean 68% of your data falls within this area. Of course, that's at 1 standard deviation. Now, if we want to go 2 standard deviations, okay, that would be here and here, where this is your upper limit and this is your lower limit, okay, we're using 2 standard deviations, that would mean that your data, if you use 2 standard deviations, is going to fall within this whole section, okay? And so, of course, we got these two, and that was 68%, right? We don't need to add that again. But then, now we have 13.5% and another 13.5%, right? And this equals 27, just saying that. So let's see, 95. So 95% of all of your data falls within this section where your standard deviation, or where you use 2 standard deviations for your upper and lower limits. Okay, so I hope this visual starts to make a little bit more sense is what we're talking about when you say a percentage of our data falls within these limits. Okay, so these are your limits here. We're using 2 standard deviations for our upper and lower limits, and 95% of our data falls in here. And do you kind of see how we kind of understand why there's no way we could have done this with any other type of distribution besides normal distribution? So now let me just show you how you can apply this empirical rule to an actual frequency table, or data that you actually have. Okay, so pretend you already, we're going to use our classroom example, of student grades. Remember that this class had like an N of 100, so there's 100 students, okay? So we just use this example with the empirical rule, and let's just try to get you to understand this. Okay, so all right, we already have the mean, or the mu, which is 65.5, and then we have our standard deviation, which is 14.5 right here. Okay, so, and then here we have our empirical rule. Okay, so first things first, let me show you how to figure out what your upper and lower limits would be if we use just one standard deviation. Okay, we're just going to use one of those. So 14.5. So to find our lower limit, okay, we take our mean minus, remember, because when you're finding your lower limit, you're subtracting. Okay, so then we have however many standard deviations we're going to use. In this situation, we're just using one. We're going to try one. That's the first one that we're going to do. So 1 times the standard deviation, which is 14.5 right here. Okay, and then go ahead and do your math, and we get 51. Okay, so 51 is what we have here. Okay, now let's go over here and find our upper limits. We have our mean, and then we're going to add however many standard deviations times the standard deviation, and we get 80. Okay, so 80 is our upper limit for 1 standard deviation, and 51 is our lower limit for 1 standard deviation. So that means that, okay, so what that means is that 68% of the data, or the test scores of the students, fall within scoring 51 and 80% on their test. Okay, that's what this is telling us. Okay. Why is this not? Oh well. All right, so I went ahead and put these two in here, but we haven't gotten there yet. So anyway, let's see what it looks like if we just want to figure out what would be if we use 2 standard deviations. And remember, 2 standard deviations gives us 95%, right? 95% of the data is going to fall within those limits. So let's figure out what those limits are. Okay, so we take our, let's find our lower limit first. We take our mean, subtract however many standard deviations we're doing, which is going to be 2. We're going to do 2 standard deviations now because we're figuring out this one. All right, so, and then of course we're going to multiply that by the standard deviation. Okay, so we work our math out and we get 36.5. So 36.5 is our lower limit for 2 standard deviations, or for our 95% range. So then we find our upper limit, which means we're going to take our mean, we're going to add however many standard deviations we are trying to figure out, which is 2, and then we multiply that by the standard deviation, okay, and then we get 94.5. So 94.5 is gonna go right here. This is whatever we get. This is our upper limit for having 2 standard deviations. So what this means is that this section right here, those limits cover this entire section. Okay, so, and remember this entire section is 95%. So that means that 95% of the total scores that the students scored on the test falls within 36.5% and 94.5%. 95% of the scores, 95% of your data from the students is going to fall within that range. Okay, and that's what it looks like. So of course we still have, you know, these little small sections of data that aren't included yet. So let's figure those out. So how we would do the next batch, okay, would be exactly the same way. All you're going to do is take your mean, okay, take the mean, and either plus or minus, depending on if you're finding your upper or lower limit, and you're going to add that to however many standard deviations you're going to do. So if we're doing the third one, okay, that's just going to be 3 times whatever your standard deviation is, and then just figure that out. So I went ahead and just did this on my own. For the upper limit, using that formula, we got 109, and for the lower limit, we got 22. That means that this whole section right here, okay, covers, what was it, 90 something, 90, is it 99.7% of the data, I believe? 99.7% of your data, okay, is going to fall between 22% and 109%, you know, between those two scores, okay? So that's pretty crazy, okay, that we can figure things like that out. Now let's go ahead and look at some, you know, questions that can be asked about this type of a situation. Okay, so question, what percent of the data, or, you know, student scores, because that's what we're looking at, are between 36.5 and 80? Okay, well, look, 36.5, wait, let me go ahead and erase all this to make it easier. So 36.5, which is right here, and 80 is right here. That would mean this whole section of data. Okay, how would you figure that out? You would go 34 plus 34 plus 13.5. Okay, so which would be, because you know that this is 68. Give me 1 second. Can't add today. 13.5. So 81.5% would be the percentage of data or, student scores that are between 36.5 and 80. And that's how you would figure that out. Okay, another thing I want to for you guys to remember is that this entire thing, remember I told you to think about it like percentages, this entire thing is 100%. Okay, so all these percentages here are going to add up to 100%. Okay, so anyway, so another question that you could get asked might be what cut point marks the top 16% of the scores? So that would mean the top 16% of all the scores on the test, the student scores on the test, right? Well, of course, you're going to be looking in this section, okay, and you want the top 16%. So we're going to start figuring out how much of this is the top 16%. Well, turns out if you add your 0.15%, your 2.35%, and your 13.5%, that all equals 16%. So basically, this is all included in your top 16%, right? Which would mean that this would be your cut point that marks the top 16%. So 16% of your students scored above 80 is what that means. So what's another one? Okay, so what percent of scores are below 94.5? So here's 94.5, right? What percent is below that? So this is the cutoff for 94.5, and pretty much it would be everything that is going this way. What percentage is all of this? So pretty much what you would do is add up all the percents, okay? Add up all the percents, and that's how you would figure out what is the percentage of scores that are below 94.5. But a shortcut that you could use, okay, is that you remember that this is 50, okay? And you know that that's all included, so you could just say 50 plus 34 plus 13.5, and that just kind of shortens your math a little bit, and you would still get 97.5%. Okay, so another question could be, what are the cut points for the middle 68% of the data? What's the middle 68% of the data, you ask? Remember, it's this whole section right here. Right here. Your top 34.2%. So here's your mean, right? It's 34% over the mean and 34% under the mean, right? 34% above the mean and 34% below the mean. That would be your middle 68%. Well, 34% above the mean is 80, and then 34% below the mean is 51. See? 51 and 80. Okay, these are your cut points for your middle 68% of the data. See, this is fun. This is a lot of fun. We're having fun right now. Okay, so what is the probability that if I select one student, that student will have a score less than 80? Well, where's 80 on here? 80 is right here. 80 is a cut point right at this section, right here, right? So basically what that means is right here at this point, we want less than 80. What's the probability that a student would get less than 80? It's adding up all these percentages. That is the percentage that you would get a student with a score less than 80. Remember, I told you the shortcut, you already know that 50% is this much. Okay, and then of course this is 34, so you just add 50 and 34. But if you didn't know that, you could literally just add 34 plus 34, 34 plus 34 plus 13.5 plus 2.35 plus 1.15, and then add up all that, you would still get 84%. Okay, next one. What is the probability I will select a student with a score between 36.5 and 51? So 36.5 and 51. What does that mean? That means, what is the probability that you will select a student who scored somewhere within this section? What is that? It would be 13.5%. Okay, we don't have to add anything up, it's just right there. Okay, 13.5% right there. Okay, so you guys kind of get an idea of how this works. Of course, with the same, frequency table and situation that I gave you. But what if in any other, scenario or study that you're conducting, what if who knows, what if your mean was exactly the same, but your standard deviation was different? What if it was larger than 14.5? Okay, what if your standard deviation was 20? Okay, what would that do to your intervals? It would make them larger. Okay, your intervals would be so much bigger. Basically, these intervals would not be what they are. Okay, what it would look like is, let's say your, like we said, your mean stays the same. So this is still 65.5, but your standard deviation is now 20. What does that mean? That means that this is going to be 65.5 plus 20. Okay, so what is that? That would be 85.5. Okay, that would be your that first interval, or after the mean. And same thing over here. This would be 45.5. Okay, so if your standard deviation is higher, then your intervals would be a whole lot wider. Okay, these would be way wider. All right. Also, this one would be way wider, and there would be, it would be a lot closer to 100. Okay, so like this one would turn into, it would be 65 plus 2 standard deviations, which would make it 40. What's 65 plus 40? That would be 105.5. Okay, that would be this one. Okay, so we're already going past 100 at this point. It's getting really, really wide. And then this one over here, that would be 65.5 minus 40, which would make this one 25.5. Okay, so it would be a whole lot different. These intervals will be way, way larger. Okay, now what would happen if your standard deviation was smaller? Well, I'm pretty sure you can guess that the opposite effect would happen, right? So if it was smaller, if it were 10, your standard deviation were 10 instead, so it would look something like this. Like your 65 would be the same, but your first upper limit would be 65.5 plus 10, which is 75.5. And then your lower limit over here would be 65.5 minus 10. Okay, so that would be 55.5, right? Or something like that. And you would just work it out in the same way. Basically, what's happening is if your standard deviation gets smaller, then the width in your chart gets smaller. Okay, actually, what this curve would start to look like is you're going to get a more of a steeper normal distribution. okay? Whereas when it gets bigger, when your standard deviation is wider or bigger, it's way more wider. So it's more like this, you know? So here's another reminder, because I hope I explained this earlier, or someone explained this earlier, but the entire thing, of course, equals 100%, right? So that means that each percentage, or each section of here, the percentages refer to the percentage of the area of the shape. Okay, so this is just the 34% just refers to this area of the shape. So it's just 34% of this entire normal distribution curve. That's what that means, 34% of this whole thing. Okay, like I said, imagine that the whole thing is 100%. So, for example, the orange part is 35% of the area, right? 35% of this entire thing. It is also the probability that an x between mu and mu minus 1 standard deviation and mu minus 2 standard deviations will be selected, or mu or mean, same thing, right? So it's the probability that an x, or a score from the student, because we're looking at student scores in this situation, that a student's score will fall between the mean minus 1 standard deviation and the mean minus 2 standard deviations. Okay, it's the probability between that, and we kind of demonstrated that in the previous questions. Okay, so conclusion. The empirical rule allows us to establish intervals that apply to just normally distributed data, okay? Normal distributions only, okay? And then these intervals have a certain percentage of the data points in them, okay? And we've seen that just by looking at that flow chart, okay? These intervals depend on the mean and the standard deviation of the data distribution, and that is why it's so important to get your mean and your standard deviation, and that is going to help us with the distribution of the data.